With this topic, I'm going to lay the theoretical foundation for exact differential equations. And so if you need a review of partial derivatives, go back to my previous video. Otherwise, I'm going to assume you know what you're doing with partial derivatives. Alright, so here's the idea. Let's start with a function equal to a constant in 3 dimensions. So, and we use z and f of x, y interchangeably. Alright, so what I'm doing is I'm going to build a certain kind of differential equation, one which we can solve by figuring out what this is. So actually I've started with the solution to my differential equation first of all. Alright, now in the multivariate theory, the differential of z up here, the differential of z is going to be the partial derivative with respect to x of our function times differential dx plus partial derivative f with respect to y, differential dy, and the right side of the differential c will be 0. So I've taken the differential of this little equation and created a differential equation. Now, we know that, and by the way, if you're wondering where that comes from, it sort of resembles a product rule, doesn't it? The theory is covered in your book. I think it's in lesson 6. You can find it there. It's also covered in a multivariable calculus course. So I won't spend time justifying that at the moment. But the other thing we know is that if this function is continuous over a simple closed region, maybe it's a simple open region, I have to look that up again. If there's nothing funny going on with this function, it doesn't have some breaks in it due to division by 0 or what have you, then we also know that the mixed partial derivatives are equal. In other words, fxy is equal to fyx. Okay, so here we go. We're going to need this result here in a minute. Now, written as a differential equation, exact differential equations are, we speak them in these terms. P of x, y, dx plus q of x, y, dy equals to 0. Now, you've already seen differential equations like this, particularly the ones with the homogeneous coefficients have this form. The ones with the linear coefficients have this form. But what we're after is a certain type of differential equation that is called exact. And partial of this function, z or f of x, y, depending on what you want to call it, partial respect to x is equal to pxy. So since partial f respect to x is equal to p, if I take its derivative with respect to y, then I've got a mixed partial derivative here. I've got literally fxy. X was done first, y was done second. Fxy is equal to partial respect to y of p, or p subscript y. Similarly, if I go over here and take the partial with respect to x of the partial respect to of f with respect to y, then this is the partial with respect to x of function q, or this would be qx. And so and notice that qx is equal to what? I'm running out of room here. This is f yx. In other words, the y derivative is taken first and then the x. Because of Clairaut's theorem, if f is a function that's continuous, then these are equal. And so, in other words, if Py is equal to Qx, then this is an exact differential equation. This is an exact differential equation. Now, what I really wanted to say, I didn't have room to write it, was that if that's true, then this function exists in the context of this equation. All right, let me give you an example of this real quick. So we're in lesson 9, and we'll find a problem here. Let's try number 4. Number 4 on page 79. Okay, so I'm going to erase this. But here's where we're headed. If this is an exact differential equation, then all we need to do is figure out what z is. Z will equal to a constant. And so let me show you that technique. Like I said, this is problem 4 on page 79. And let's read through it. Parentheses 3x squared y plus 8xy squared dx plus parentheses x cubed plus 8x squared y plus 12y squared dy equals to 0. So it's a first order linear differential equation, but it does not have linear coefficients, and it's not homogeneous. Now these terms are degree 3. 2 plus 1, 3. 1 plus 2, 3. These are degree 3 terms. These two are degree 3 terms, but this is degree 2. And so trying to solve this by using the homogeneous coefficient method is not going to work because we don't have those uniform degrees in those polynomials. So, next question is, does it fit the exact differential equation template? And so this is function p dx plus function q dy equals to 0. So we check to see if it's an exact by taking the partial of p with respect to y. Alright, so I'm treating x as a constant, taking the derivative with respect to y, I'll get 1 times 3x squared plus 2y times 8x, 16xy. And now I'll take the partial of q with respect to x, and here I'm treating y as a constant, taking derivative with respect to x, so here is 3x squared plus 16x times y, 16xy, and this derivative with respect to x would be 0. So look what I have. Partial of p respect to y equals the partial q with respect to x. Now, if you just made up stuff, that's normally not going to happen. So this only happens under the right circumstances, under the right conditions. But it's important enough to consider here in this course because this is related to conservative force fields in vector calculus. So I think it's well worth looking at. Alright, because these partial derivatives are equal, that means they came from they're mixed partial derivatives of another function. In other words, this means then there exists, by the way, the capital backwards E means there exists a function z, or f of xy, such that, and here's a little symbol for such that, so here's there exists and such that. I'll use that from time to time. So then there exists, it's just mathematical shorthand. Then there exists a function z equals f of xy such that zx is equal to p and zy equals to q. Now, if you're kind of new to partial derivatives, then notation is kind of bewildering. I could write f of xy, f of x, f sub x, this is what I meant. I could write f sub x and f sub y here. I could use the partial derivative notation. The idea is that because this is true, that implies that there was a function up here such that p came from the first derivative with respect to x of that function and q came from y. Because, again, if I now take this partial respect to y and this partial respect to x, they're supposed to be equal, right? Mixed partial derivatives are equal regardless of the order. And this would be py and qx. Py, qx. All right, we verified all that. So, we verified that this is an exact differential equation. So, this is an exact differential equation. All right, now once again, what's the big deal about that? Well, all I have to do is figure out what this function is, z. And how in the world do we do that? So, well, once I verify it's an exact differential equation, I really don't need this. So I'm going to erase it.